So here we go. And by the way, we need 225. The chain rule. And this is section 14.5. And I almost think maybe the thing to do is to just do a quick check exercise with you guys. I know you haven't seen these yet. There's no way. With your test and everything else you have. I think that might be a great way to start, is just see an example. And then we can get into some of the nitty-gritty. It's funny. I like this chart. They say for you econ people, although I didn't see one econ person in terms of writing down that economics is where you said you wanted to go, the sheet at the beginning of the year. And yet, who knows? Maybe someone will do it, because it's a great thing you can do with mathematics. There's a lot of jobs out there. Productivity is a function of labor, capital, and resources, correct? Does it depend on all those things? Sure, Paul, if you say so. Okay. Labor is a function of unemployment. Is that true? Okay, as unemployment goes up, maybe okay. Well, yeah, they're related. Capital depends on the interest rate. Is that true? Maybe if interest rates are higher, people put more in the bank? Maybe. Resources depend on time. So you get this functions of functions going on. Okay? And that's what the chain rule is all about, is a composition of functions. All right. So they're going to go through cases, cases, cases. The chain rule with one independent variable, several independent variables, and then, there's something from the past. Do you remember what's called implicit differentiation? We studied that right after the chain rule. So I don't think I'll get to that today. I think I'll have to wait till next time to talk about implicit differentiation, which is good. But the chain rule, let me just clear this up. When I say independent variable, do you guys know what I mean? That's right. When we say with one independent variable, right, that's just x, right? But then when we say with multiple, I guess the opposite of independent is dependent, right? So in Calc 1, y depends on x. But in Calc 3, what happens? Yeah, let's do this. Let's say that usually z depends on what? X and y. So z is a function of x and y. And so when I'm looking at your book here, and they say the chain rule with several independent variables, I think that's where I want to go. Okay? But even the chain rule with one independent variable is an issue because, by the way, remember Aaron was talking about introducing u? If you introduce u, you can write the chain rule in this really slick way. Did you guys ever see this? dy dt is dy du times du dt. That's Leibniz notation. That's really ding and dong, dy du and du dt. So now, yeah, they're going to bring up these tree diagrams, but I want to do an example. Yeah, that's okay. Example 1. Let's do one of your homework problems. Yeah? No, that's not what I want, guys. Okay, let's do an example. Here we go. Where'd that example go? Lost it. Chain rule with one independent variable. Here we go. z equals x squared minus 3y squared plus 20. Let's do that. Z equals x squared plus, oh no, x squared minus 3y squared plus 20. And they tell me x equals 2 cosine t and y equals 2 sine t. Actually, this may make some sense to you. Because what we have here, guys, is a set of parametric equations, right? X depends on t and y depends on t. You can graph that, right? What's that look like? That's a circle, right? So as time goes by, we're moving around a circle of radius, what? 2. If it was a unit circle, it would just be x's cosine and y's sine. And now the z value, what is the z? I don't know. Maybe it's production, depending on x and y. I don't know. It's some function. So here's my z function. And now we want to compute some things about it. We want to compute some partial derivatives and also interpret them if we can. Find dz dt and evaluate it when t is pi over 4. All right, here we go. So dz dt equals, well, z isn't a function of t directly, is it? It could be. If you substituted in the 2 cosine t and the 2 sine t, I guess you could turn this into a Calc 1 problem. Then you'd be done. Okay? The problem is, usually, can't substitute in. I mean, you could, but you wouldn't want to, and it wouldn't necessarily work. Okay? So, yeah, maybe we'll do both. But what we are going to do is we're going to say that dz dt is equal to dz dx. Oh, wait a minute. I just screwed up. I'll show you what I screwed up. This must be written as a curly d, because this is what kind of derivative? It's a partial derivative. How do I know it's a partial derivative? Because z is a function of more than one variable. Times dx dt, those should be written with regular d's because x is a Calc 1 function. Plus curly d z dy times dy dt. Regular dy dt. So that's the chain rule. The chain rule says this is the rule for the derivative of z with respect to t. All right, here I go. dz dx is going to be what? That's correct. 2x times dx dt would be negative 2 sine t, because that's the derivative of 2 cosine t, plus dz dy, I'm going to have negative 6y, right? I take the derivative, everything else zeroes out, times 2 cosine t. All right? And now they say, let's compute dz dt when t equals pi over 4. What does that equal? Well, okay, I have a little bit of work to do here because I need to write down 2, and then I need to substitute in x. But do I know what x equals? Well, I can work it out, right? When t is pi over 4, then I'm here. What's the cosine of pi over 4? Radical 2 over 2. And I'm multiplying by 2, so I think I get a radical 2 there. And then times, now we have negative 2 times the sine of, what's the sine of pi over 4? Yeah, radical 2 over 2. So they were really nice to me. Okay? Plus, here I have negative 6 times y. This is 2 times radical 2 over 2, so radical 2, times 2 times radical 2 over 2. So it seems to me lots of stuff's canceling. All right, let's work this out. I'm getting radical 2 times radical 2 is 2. Those 2's cancel, so I'm getting negative 4. And then I'm getting minus 6 times 2 is 12, and the other stuff cancels, so minus 12. I'm getting negative 16. Okay. How the heck do I interpret this geometrically? Well, I guess as time goes by, right, z is decreasing. Well, it's decreasing when t is pi over 4. So when I'm right here, and we know the motion is traveling this way, because that's what happens around the unit circle and also around, what would you call it, the double unit circle? When I'm right here, my z value is decreasing. Okay? As I'm moving this direction. And we'll check the solution, and then we're out of here, guys, because I'm right at the end of class time. They do what we did pretty much. Oh, they used a nice trig identity. And they also substituted back in for the x and y, which is interesting, but they got the negative 16. Yeah, it's good to see. And then they have a really nice picture of it. Yeah, that's worth looking at too. Let me jump to t equals pi over 4 so we can see it. There's the decrease, guys. You could see we were going around this curve on the unit circle, and now you can see z is dropping at this point. All right, nice work today, guys. Okay, like I said, last time we were here, we were working on the chain rule, and we did an example that involved partial derivatives and regular derivatives, right? Because we had this z was a function of two variables, x and y. Okay. But what I want to do today is I want to revisit an idea from Calc 1, which is called, maybe I'll do it on a new page, implicit differentiation. And so what happens in implicit differentiation, the classic example that I like to use with my Calc 1 students is I give them this. And I say, okay, if you graph that, what shape is it? It's a circle of radius. And one of the reasons I do that is so we can plot lots of points, right? Because if it happens to go through things like 5, 0, and 0, 5, one of the nice things is it also goes through things like 3, 4, which makes it a great Calc 1 problem. Okay? And so I might ask you guys, oh, it's coming back. I might ask you guys, what's the slope of the tangent line at these various points? And because we've learned how to do derivatives, we all say, oh, I can do that. And then we say, oh, wait a minute, maybe I can't. Because in Calc 1, we take derivatives of functions. But what's the problem here? A circle, in general, doesn't meet what? The vertical line test, so it's not a function. But if you think about it, calculus is really done at what they call the local level. I mean, it's all about epsilons and deltas, right? And if you use your zoom feature of your notebook paper, you'll find that, the tangent line I care about going through 3, 4, that really does look like a function. And so even though I don't have a function per se, implicitly a function is defined locally. That's kind of the idea behind this. Now the process you might remember. Do you remember the process, what you do? Implicit differentiation, you would take the derivative with respect to whatever variable you want, usually x, of both sides. You guys remember that? So then what did you write next? Well, I'll do the right-hand side for you guys, because you may not remember. Okay, you guys do the left-hand side. What do we get?
2x plus 2y dy dx.
Very nice. Matthew remembers, dong, the chain rule, right? So actually, that's when we teach it in Calc 1, is right after the chain rule, we show them implicit differentiation, which is a nice application of the chain rule. And then the idea is, if you want to know the slope of said tangent line, what do you do now? You solve for dy dx. So you get dy dx equals, well, I guess if I subtract 2x and then divide by 2y, I get negative x over y, right? Which is a formula for the derivative, but it's the first time we've ever had a formula for the derivative in 2 variables, right? And so what happens is you use it and you say, okay, here's the point 3 comma 4, and so the slope of that tangent line is negative x over y, negative 3/4, and it turns out to be right. So that's really kind of cool. We don't really understand why it works or care, other than everything I've been doing seems very legitimate, right? Taking the derivative of both sides is allowed. And if we understand the chain rule, I guess that's why it works, okay? But there's another way you can think about this now that you're in Calc 3. And so I'd like to do that now. I'd like to take the equation that I have, and I'd like to point out that you can take this equation and you can solve it for 0. You could say x squared plus y squared minus 25 equals 0. That's the same, right? That's the same equation. It has the same graph as the one we used before. And as a matter of fact, what I might do is I might say, okay, f of xy is going to be the function x squared plus y squared minus 25. Because I want to do Calc 3 for a moment. You see that? And what I end up doing then is I think of this. This is a level curve. There they are again, guys. They don't go away. Of f of xy, right? It's the level curve corresponding to, well, c equals 0 if we use the, right? Problem 67 is one of yours. This is where I think I really better continue on this, because you can take implicit differentiation up a notch, up another dimension, okay? And that's what I want to do. So I need to explain this a little better. But 66, I noticed, I think will help us. There's some nice geometry that goes along with implicit differentiation. So I'll try and recover that for us with our example. Okay, so we'll see if we can do that. Again, the new approach to implicit differentiation is this. In general, if you have something like this, f of xy equals, in our example, we had it equal to 25, right? We had x squared plus y squared equal 25. But in general, I don't know, you'll have this, right? G of xy. What you do is you set the equation equal to 0, and so you get big F of x comma y equal to 0, right? That's the approach.
And big F is F minus G.
Yeah, I guess it would be big F is F minus G, right? And the point to make is that when we do implicit differentiation, remember my zoom that I showed you guys? We're thinking of y as a function of x. That's really what you're doing. Okay? So then the next step is we say, let's take d dx of both sides. Only I guess what you're really doing is, again, partial, because that's a function, right? So, and this is where, again, the book, I think, has the argument better than what I was saying with the example. There it is. On the left-hand side, df dx 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 df dy dy dx. That's the chain rule. Let's write that down. The partial of f with respect to x times dx dx plus the partial of f with respect to y times dy dx. Okay? When you take the derivative with respect to x of both sides, you need to use the chain rule. Of course, here, dx dx is going to equal what? 1. So the new equation we get is this. And now it's convenient to switch back to Newton's notation. We kind of use the different notations where and when they're convenient. So this is fx times 1, right? This is fy, right? And this, in Newton notation, is y prime, right? That's the thing we were interested in. We wanted to know the slope of a tangent line for the circle. Remember that? And so what we do now is we solve, and we get that y prime will always equal negative fx divided by fy. That's what it'll always equal. So back to my example. Now that we have our magic formula for implicit differentiation, back to the example. We had x squared plus y squared is 25. We said let's write it as big F of x, y, is x squared plus y squared minus 25. So that's big F. Notice that fx is 2x, and notice that fy is 2y, right? And so my formula, again, y prime is negative fx of xy over fy of xy. These are functions of x and y in general, although in our example, fx is only a function of x, and fy is only a function of y. That's what they are. But there you have it. Okay, so we get negative x over y again. And that worked again. Okay. And before we leave this example, I want to go again to your book that problem 66, I think, is worth us talking about in class. The geometry. Suppose x and y are related by this equation f of x, y equals 0. Well, they are. That's what we have. Interpret the solution of this equation as the set of points that lie on the intersection of the surface with the xy plane, z equals 0. I want to draw a picture, because that's what part A says to do. Make a sketch of a surface and its intersection with the xy plane. Well, can I graph this thing? Let's see. What's the function? The function is, again, f of xy, or z, is equal to x squared plus y squared minus 25. Well, let me draw some axes, I guess. Okay. Actually, for this one, I think I really want to go low. How low do I want to go on the z-axis? I guess if you were at 0, 0, yeah, that'd be a point on the, right? So one of the points would be 0, 0, negative 25, right? But if I go all the way up to either 5, 0, 0, or 0, 5, 0, right? I see that in the xy plane, I have a circle, right? Which, if you want to make a circle look three-dimensional, you draw it like an ellipse, I was told. Are you with me on it so far? Do you know what shape this thing is? X squared plus y squared minus 25 equals z? I would call it a, you know, if we set y equal to 0, it's just x squared minus 25. That's a parabola, so I would call this a paraboloid. It's kind of a parabola spun around the z-axis, right? So there's just, you know, part of it, but kind of comes up in all directions, and the circles get wider as you go up, right? Does this start to give you a flavor for what it looks like? My high technology legal pad here. So I guess we did it. With this circle, the curve, we can now, you never would have done this in Calc 1, but you might think of any curve in the plane as the level curve of another surface. And now, because I know Calc 3, what am I really doing? I'm saying that the slope of the tangent line, which again, I guess it was at 3, 4, that'd be right here, 3, so we were finding this slope of this tangent line, right? And somehow, the way to get that is negative fx over fy. Now let's go through what those things are. Fx, what's that mean? That means you hold what fixed? Because I'm asking. Oh no, you're right. We hold y fixed. So for a particular y value, and this is where the book is better than I am, they have these planes, right? And the question was, if you intersect that plane with the surface, then you get some, I have to think, if I chop the paraboloid in half with the plane, I would have another kind of parabola here, right? Let's see what else it asks me to do. Give a geometric interpretation of the result that y prime is negative fx over fy. Explain geometrically what happens at points where fy equals 0. Well, maybe we can do that for our example. What happens when fy equals 0? That's holding x fixed, right? So that would be holding x fixed at 4, looking at this plane, and if fy equals 0, oh, that's weird, then you can't compute y prime, right? Our formula doesn't work. Where would fy equal 0? What is fy? Fy is 2y, right? So I guess this would happen when 2y equals 0, when y equals 0. Do we have any points where y equals 0? Yeah, we do. Like this one, right? Oh, okay. So that point there, 5, 0, 0, if I look at its tangent line, right? Well, that's a vertical line in Calc 1. It has no slope. And again, if I had a fixed x, there, I guess that would be a plane like this. So here's an exercise to try for just a second here, okay? Remember how we wrote down f of x equals x, y of x? And then we took the derivative of both sides? We just did this. What you guys have to do now, there's a third variable involved, right? And it says, see if you can show that this is true. The partial of z with respect to x if y is fixed is what that means. It's a new notation because remember that these are functions of x, y, and z, just like f is a function of x, y, and z. What I want you to do is see if you can use the chain rule to get part A done. And if you can, then I feel like I can turn you loose on this problem. If you can't, I will show you how to do it. That should buy me just enough time to do what I think is worth our time. All right? So, it turns out, if you really want to understand the geometry in this problem, you need the tangent plane, the plane tangent to this paraboloid. By the way, the plane, I mean, if it were at the bottom, it would be parallel to the xy plane, right? If it were over on the side, it's hard for me to show you, but do you guys see it would always be slanted upward as I rotate around the paraboloid? It would have a bend to it. And what you guys really need is you need to know that plane and how that plane intersects the other planes I've been drawing. And the problem is we're not studying tangent planes until Monday. Tangent planes. But we will. And then it turns out that those planes, that kind of gives you some visualization as to what's really going on here. Yeah.
Can't you just use the equation of a plane? As long as you have the point and the vector, you can find...
Exactly. And so the vector is going to be what we call the normal vector, and it's also normal to the surface. But what we're about to see here, if I can do the rest of today's lesson, is that the normal vector, well, I think I can. 15 minutes is enough. The normal vector comes from the partial derivatives. Yeah, it's really nice. So here we go. By the way, I did want to give you a hint on number 67, so let's do that. Problem 67 says, okay, f of x, y, z equals 0. We're going to differentiate it with respect to x to show this thing. Okay. So here's the start of that. F of x, y, z equals 0. So again, this is kind of weird, right? This is where, suppose you want to find a tangent plane. Okay? And so you're going to use implicit differentiation, but we're upping it a dimension. Now we're here. So chain rule says what? It says this: fx times dx dx plus fy times dy dx plus fz times dz dx equals 0, right? So let me explain what I did here. This is number 67 on the homework, part A. I took what of both sides? Partial derivative with respect to x. Why didn't I write any other curlies? Because I thought it would be a lot cleaner if we just wrote capital F with a subscript. You guys okay with that? Okay. Maybe that's a bad idea, because what problem 67 says is, here, show that dz dx when y is fixed is equal to this. It says, note, that subscript does not mean derivative. So what is it that I'm solving for in the equation? Yeah, that's dz dx, but we're going to put a subscript y, which means y is being held fixed. Now, if y is fixed, that actually implies something. It implies that dy dx is 0. Okay, let me fill in everything else. So everything else, actually there is one more thing I know. Dx dx is still 1, like it was in the Calc 1 problem. Oh, okay. So we get a formula. We get this dz dx, curly dx when y is fixed, is equal to, I guess it's no, it's the other way, right? Hang on. Negative fx over fz. So, okay, so I guess, shoot, it's the other way. This is what I'm solving for. This is dz dx with y fixed. That's what I'm solving for. And I see, my other error, guys, was once again, I didn't make these curly. Why should I make them curly? Because implicitly, z is a function of both x and y. See that? Just like y was a function of x, z is a function of x and y, but we're going to hold y fixed so that we have something to say. All right, so now, wow, that's messy. There they are, guys. We get negative f of x divided by f of z. Part A is done, and you can try part B and beyond this weekend. Okay. Time for